Hello?
Hi.
Hello?
Hello.
This is Mohler Thompson Summer Research 2020, and the summer researchers are Dr. Mike McDaniel
Joshua Wierenga.
and Coco Bananas. She's with us today. And our topic is an interesting topic because we're timely. We're studying the geometric structure of viral capsids. So the capsid is the casing for a virus. We've got two models of them here, and we're trying to study it using elliptic geometry because elliptic geometry allows you to be in a flat world and a round world at the same time. And the virus itself is not a dodecahedron. It's not an icosahedron. It's puffy. It's rough. And my geometry, or the application of elliptic geometry, helps capture that. So let's take a look at what we're working on. So here's what inspired the paper, or our summer research work, I'm sorry, is a paper by a guy named Dave Wilson. He's a professor at Kalamazoo College. And this is a famous drawing in mathematics by a geometer named Coxeter. It's the icosahedral sphere. And what's supposed to be the case is, see that yellow triangle right there? That's the same size as this triangle here. You can see that those two are the same. It's also supposed to be the same size as this triangle here. And this triangle here. Anybody with a blue and two greens, any of those triangles are supposed to be congruent. Well, I had a slight problem with this because, this triangle doesn't look congruent to that one. Now, what you're thinking is, well, it's on a giant beach ball. If you turn the beach ball, this triangle looks like it's congruent to that one. And yeah, I agree. But I could do better using my elliptic geometry. So let's just keep this in mind while we look at the first thing that Josh and I did, which was to build the models in Zomatool, which is this toy. Go ahead, Josh.
In Wilson's paper, he mentions that there may be evolutionary constraints on viral capsid structure. Our early results show that pentamer and hexamer, you can see pentamers right here, and there's a hexamer right here.
Yeah, one,
Yeah.
2, 3, 4, 5, 6 sides there.
And this is shown in all spherical viruses, and it makes evolutionary sense because of the way that monomers orient themselves. Large polymers are created and form in the shape of pentagons. These polymers fit perfectly together without additional macromolecules needed to complete the capsid. Can we redo this?
So our first job that I decided on was, let's try to construct in elliptic geometry the Zomatool toy that you just saw, or the elliptic geometry version of the Coxeter drawing that you just saw. Surprisingly easy. It took us a few weeks, but surprisingly easy once we got all the steps worked out. So you can see here, I start with a regular pentagon. And then I found that if I use a vertex as a center, I can make arcs of circles going through opposite vertices. Those are actually going to be elliptic lines, and they give us, and this is an amazing coincidence, this angle right here. This angle is 72 degrees, which is the angle we need. We need 72 degrees here, 72 degrees here, and 72 degrees here, and we got it. That's simple. That was an amazing coincidence. Now, we had to come up with the boundary circle for the space so that these arcs count as elliptic lines. Well, that wasn't too bad. It was a very simple move. This darker circle out here is the boundary circle for elliptic space. So here's elliptic space. And if you think about it, I've got 5 triangles in here. I need to get the rest of the space tiled with triangles. And here's what happens. You extend any 2 sides of the original pentagon out to here, use that point as a center, and make a circle through 2 non-consecutive sides opposite. And that circle, as you draw it out to the boundary, gives another segment of the rest of the triangle. So you see these little pieces coming out here? You do those all the way around. And when you're done, you have the exact model. Now, we wondered, that was too easy. Does this sort of structure, do these steps work for, say, a 7-sided polygon or a 9-sided polygon? Because what makes it all snap together is, and Josh worked on this, there's this exterior angle here whose size is very important to how the rest of the triangles are going to fit together. There has to be a certain coincidence that happens with 5 sides. we wondered, does this happen with other numbers of sides? So Josh's assignment was find the size of this angle here, this angle that looks like this. Find the number of degrees for that angle. So let's see what Josh did.
So to find the exterior angle, we created these systems of equations. Each variable, which is 4 unknowns, is just another angle in our model. When we solved this, it proved our conjecture, which is this, n minus 1 over 180 over n. It basically proved that each interior and exterior angle of the pentagon, our structure over here, it only works for n equals 5, which is perfect, and any other variable would not work.
Now you're looking at a color print of an idea that I had, which was take the model that we can construct, that we actually proved has these nice properties, and then say, what if I could see the other side of the virus at the same time? Because it's the case that one side of the virus determines what the other side looks like. The structure of the other side is already completely known, and in fact, the other side of the virus capsid is the same as the side you're looking for, except upside down. So we took the construction that we had, took a copy, flipped it, and pasted it onto there. So that's why now all of a sudden you see that there's two different pentagons around the center. There's a red pentagon and a blue pentagon around the center, because you're looking at both sides of the virus capsid at the same side. And I did the same thing with those other lines that go from these triangles outward. So there's actually, like if you look at this blue triangle here, it looks like it's two pieces, but in elliptic geometry, this is actually true, that this vertex is treated at the same as that point. They're the same point. This segment here is the same as this segment here. So what happens is this blue triangle is completed over here, and this blue triangle, this one blue triangle, has three angles of 72. This is 72, this is 72, and this is 72. So I can see all the triangles, the front and the back at the same time. And here's what's very exciting about this. By keeping all, you see these thin lines, those are the continuations of the segments that are on either this side of the world or the other side of the world at the same time. These thin lines end up being related to the thicker lines in ways that apply to elliptic geometry theorems that already exist, including the theorem that Morgan Nissen and I got last summer. So we are guaranteed to come up with some theorems about the placements of these triangles, like this little gray triangle here, or the blue triangle, how they are related to each other, how they're related to other of the lines that are in this geometry. And because of Wilson's paper that says that the protuberances, the things that are the sensors and the spikes on the outside of the virus, that they're on the icosahedral great circles, those are these things. So we can say more about where the protuberances are than he already knows, because we're paying attention to exactly the things that the protuberance is on. So that's what we're working on next, is coming up with as many geometrical properties of these guys as we can get. Thanks for paying attention. Bye.